Hello, good afternoon, good evening, good morning, or whenever you happen to be watching this video. All right, so in class we covered a brief overview of the syllabus, but now I'll have a first lecture for MENG 30 through 10 over course material. So the objectives for this lecture are: first, define fluid mechanics; second, differentiate between gases and liquids; third, identify appropriate units and dimensions; fourth, discuss fundamental properties of fluids; and five, compute common fluid properties such as density and specific weight. All right, so I'm going to do just that. All right, so let's begin. Now, first of all, I wish to actually define precisely what we mean by fluid mechanics. So when I say fluid mechanics, obviously you get images in your head, probably of things like, maybe dams, maybe hydraulic systems, maybe aqueducts, any sort of system involving, typically what you're probably thinking of, at least at first blush, is water. But of course, we want to discuss, and we will learn about things much broader than this. So let's provide a formal definition for fluid mechanics. So it is the study of the behavior of liquids and gases. So I'm going to write this out and then I'm going to sort of deconstruct it. Liquids and gases at rest or in motion. This is my definition of fluid mechanics. So when I say, so let's deconstruct this a bit. Well, when I say liquids and gases, what do I mean by that? Liquids and gases. Well, obviously when most people think of the word fluids, they're thinking of a liquid. But for our purposes, a fluid will be any liquid or gas. And at rest, this would be fluid statics. And in motion, this would be fluid dynamics. So we're going to be working with both fluid statics and fluid dynamics at various points through the semester. All right, so let's look at a few things. First, I want to discuss what exactly is the difference between a solid and a liquid. Now, this is sort of a review from basic chemistry, but it does help to break things down in review. So solid, now you've probably heard a definition from, you've learned definitions of solid and liquid going back to grade school, but I want to give an engineering definition of solid versus fluid. So we're going to classify matter as either solid or fluid. Fluid will encompass both liquids and gases here. So I'm going to define a solid versus a liquid, versus a fluid. Solid and a fluid here. And how I'm going to define a solid is I want to define it in terms of engineering terms, in particularly stress and strain. So I want to define a solid as something that can resist shear through static deflection. Through static deflection. Through static deflection. In other words, it has an internal capability to resist shear forces. A fluid cannot do that. It cannot resist shear through static deflection. In other words, it's going to need some sort of container to hold it effectively. So it cannot resist shear through static deformation. Instead, it deforms continuously as shear is applied. It deforms continuously as shear is applied. So in other words, when I say it deforms continuously is when I apply a shear force to a fluid, it's just going to keep on deforming endlessly. Now, a fluid is perfectly capable, though, of resisting a normal force. If I have a tube and I fill it full of fluid, I can apply, say like a piston or something, I can apply a normal force to it and it will resist normal force just fine. It's that it cannot resist a shear force. Now, at rest, however, a fluid experiences, so in other words, at rest, a fluid experiences no shear. No shear. And we will call this, there's a special name for a fluid at rest again, we will call this the hydrostatic condition. The hydrostatic condition. So if you remember from mechanics, if you remember stress blocks from mechanics and materials, and if you haven't had mechanics and materials, it's not going to be essential to this, but I just want to illustrate the topic for those who have taken mechanics and materials. So if you have a fluid, and I'm going to draw fluids with a surface and my little triangle here, how I'm going to draw in this class, if I draw a triangle with a couple lines below it, that means that there is a surface at that interface, at that line. So if I take a little element out of this bulk fluid and draw this here and then look at the stresses on it, let's look at the stresses on this fluid. And I will see that there will only be normal force present on this fluid. And in particular, I will have the same force acting on all directions. Now, that is assuming this element is small relative to the depth of the fluid. If the element is large, then obviously the pressure higher up will be lower than the pressure, or that will be lower than the pressure down below. But we're talking, when I say a little element of fluid, I'm talking about a differential element like you would see in calculus class. So again, you're going to have sigma 1, a normal stress, equal intensity in all directions. Equal intensity in all directions. And I can extend this even further if I draw Moore's circle. Moore's circle, if you remember from mechanics materials again, for hydrostatic condition. For hydrostatic fluid, it's the entire Moore circle is actually going to collapse down to a single dot. So if I try to draw my Moore circle with a shear and a normal axis, with normal stress and shear stress, sigma and tau, I'm going to simply have a dot here, sigma 1, with it being negative stress because it's obviously going to be compression from the weight of the fluid. So this would be, again, the hydrostatic condition. And again, Moore's circle collapses down to a single point in the hydrostatic condition. So let's look at a few engineering applications of fluid mechanics. So it's important, this is a foundational class for both civil and mechanical engineering, but it's especially important for mechanical engineering for basically almost everything you're going to do in your careers. Well, I suppose even things that you wouldn't think about in terms of simple machines, and even if you're designing, even things that you might not think of as fluid mechanics applications, like say designing an automobile, even then you're dealing with things like radiators and that kind of thing, cooling devices. Fluid mechanics is essential, or even if you're talking about, say, aerodynamics, the design of automobiles for aerodynamic purposes, streamlining, that kind of thing. So it appears in numerous places in mechanical engineering, which is why this course serves as prerequisites for so many of your later courses. So let's look at the engineering applications. This class is a prerequisite for many later courses, including your thermo, your heat transfer, and other courses that you'll have over the next few semesters. Hopefully not next few years, but you never know. Engineering applications. So let's look at this. A few ones that pertain to mechanical engineering, things like blood flow, pumps, and we will talk a bit about pumps in this class, pumps, fans, turbines. So pumps and fans are both essentially adding energy to a fluid flow, while a turbine will be removing energy from fluid flow, usually to take some of the energy from the fluid and transform it into electrical energy. Airplanes / jets, This is both in the fluid properties of in airplanes. They're just chock full of fluid mechanics. You have things like hydraulic controls to actually control the airplane. You have the fluid flow systems that are present in the fuel system, propelling the plane through the air. The engine, a jet engine is nothing but an application of fluid mechanics. Plus, of course, things like lift and drag and all the forces that are keeping the plane in the air. Planes are basically big piles of fluid mechanics, applied fluid mechanics. Ships, hydrostatics to keep the ship afloat, and also hydrodynamics to make sure the ship can move through the water. So in short, if I were to summarize this, almost everything is a fluid or moves. Almost everything is a fluid or moves within or near a fluid. Or near a fluid. And you'll notice as I keep doing these lectures, I sometimes periodically check to make sure the thing is still running, because I'm always paranoid that the thing will stop. If I had that mistake once I went through a whole 2-hour recording session and the thing wasn't turned on properly. I had to record the whole thing over again, so that's never fun. Again, so we've mentioned that fluids can be both a liquid and a gas. So let's differentiate between these. Let's actually break down in detail the difference between solids, liquids, and gases. Or particularly, we've already defined solids versus fluids. Let's define the difference between liquids versus gases. So liquids versus gases. Liquids versus gases. And to really find the difference between liquids and gases, and even solids, we need to look at the molecular structure. So consider solids. Let's consider solids first. They're going to have very small distance between the molecules. So have very closely spaced molecules. Very closely spaced molecules. With large cohesive or intermolecular forces. The fancy word is intermolecular forces, but this isn't a chemistry class, so we can just say cohesive forces. With large cohesive forces. So solids retain shape. Will retain their shape. So in other words, if I would have many molecules, which I'll just draw as circles here, fairly close together, and I'm going to have large cohesive forces between these. For those of you in my materials and manufacturing class, we will be studying some of this later in the semester as we get to crystalline structure, crystal cell structure, that kind of thing. So large cohesive forces between the molecules. And if you remember from chemistry class, this can be both things like covalent bonds, ionic bonds, all of that good stuff. Remember chemistry class? Wasn't that fun? So large cohesive forces. Don't worry, in this class at least I promise I won't make you balance in that ionic equation. Although I could make you do titration, wouldn't that be fun? Remember that? Anyway, large cohesive forces. Okay, so let's compare that to liquids. Well, in liquids, the molecules are going to be further apart. Obviously, that makes sense. But actually not that much further apart. In fact, let me try to draw it here, in fact. They're not going to be dramatically further apart. Like, for example, ice expands, what, by 10% or something like that when it melts? Or wait, Oh wait, that's the opposite. Never mind. Ice is actually water. Oh my goodness, water ice is actually the exact opposite of most materials. It is one of the few materials that actually expands when it freezes, which is actually a little quirk of chemistry that's totally essential for life on Earth. If water did not expand when it froze, the seas essentially would freeze over. All lakes and ponds in the winter would freeze over, and basically the planet would be entirely uninhabitable. They wouldn't just freeze over, I should say, they would freeze all the way through. Because what would happen is the top layer would freeze, it would sink, then the top layer would freeze again, it would sink, and even an ocean would freeze all the way through. So in liquid, generally, water is actually an exception here, molecules more spread out. Water is a very weird fluid when it comes down to it, which is why it's such essential to life. More spread out. So I should say, so there is more freedom to move. And even if they're not more spread out, they do have more degrees of freedom. However, it will still contain its volume. It will still conserve its volume. Is more freedom to move. But however, one crucial thing is that it maintains its volume when put into a container. But when you put it in a container, it will maintain its volume. So I'm going to draw the molecules slightly further apart, but with no cohesive forces, no large cohesive forces in between them. They obviously do have some, otherwise it would be a gas, but there are much smaller cohesive forces between them. So almost like, let me draw something like, almost like this. Small cohesive forces. Oh, I didn't need to do that. Zoom. Small cohesive forces. And mostly incompressible. In truth, you can compress a liquid a small amount, but in general, they compress. But even if you apply a large force to a container of water, it only compresses a tiny, 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 tiny fraction of 1%. In fact, in most of our cases, through the course, we will consider water to be incompressible. And finally, we have the third stage of matter that we're worried about. There are some other stages like plasma and things like that, but this is not a course dealing with, this is not a high physics course dealing with plasma, so we won't worry about that. Gases are your third primary stage of matter that we deal with. It's weird when they teach you the 3 stages of matter in grade school. They don't teach you that plasma actually composes the bulk of matter in the universe, but anyway, we're engineers, we don't deal with stars that much, so that's okay. So molecules spread out even further, and cohesive forces become negligible. And cohesive forces become negligible. So I'm not even going to draw any kind of cohesive force between them. We're going to have molecules very far apart, and even this is an exaggeration. They would be, it's almost like, to draw this properly, I would almost need to draw a circle and then put, if this was, on a computer screen or something, it's almost like I'd need to draw the next molecule in there on the other side of the room or something. So approximately 0 intermolecular force. Now in reality, it's not that they don't have intermolecular forces, it's that they have large kinetic energy relative to their intermolecular forces. So when two gas molecules collide, they try to form a bond, but they are moving so fast that the bond cannot contain the kinetic energy. And also, they are compressible. You can compress a gas. If I put a gas under pressure, if I put it in a piston, it will compress. It will reduce in volume. And both compressible and incompressible will feed into the bulk modulus of the material. Okay, so I will mention a few systems that we want to be aware of. I want to mention a few, obviously, unit systems that we'll be aware of. And this will be important, especially when we get to things like pi terms, dimensionality, and similitude, which we'll see later in the semester. So let's see. I wanted to identify units and dimensions that will be important through the semester. Identify units and dimensions. Well, of course, there are two main systems that we'll be working with. And this is the British or the imperial system or the empirical system and the SI system, the System International, or also known simply as metric. So everything is made, all of the units that we use are either primary units or they are combinations of primary units. So let me give you some, each system has primary units and then secondary units, or primary quantities, I should say. Primary quantities. And then I'll say British and SI. Primary quantities are things like length, time, mass, and temperature. These are things that have a definition in and of to themselves, and they can't simply be broken down into other quantities. These are primary quantities. Mass, length, time, mass, and temperature. Although, truth be told, we can think of temperature as proportional to kinetic energy, or average kinetic energy, but we usually consider it more of a primary quantity. And so I'm going to use, but really my main primary quantities are length, time, and mass, and everything else is derived from those. When I say, so if I ever put in brackets L or in brackets T, I'm not talking about specific units, I'm talking about dimensions. Length, time, and mass. And for the British system, the unit for length, what we're going to use is the foot. We'll be using this a lot when we get to pressure head and things like that. And for the SI system, of course, it is the meter. And you know this as well. For both British and metric, the unit, of course, is the second for time, with their abbreviations. Now, and then for the mass, well, for SI, it's very simple, of course, it's the kilogram. But for the British system, if you remember back to maybe a physics course, or maybe not, it is the slug. And temperature, we're going to need to, we may primarily use Kelvin, and Kelvin, there's no degree sign, and it is degrees Celsius plus 273.15. Now, there is actually you may not be aware of this, but there is also an equivalent to Kelvin for Fahrenheit, and that is the Rankine system. Basically, Rankine is to Fahrenheit as Celsius is, or let me get my analogies right. Rankine is to Fahrenheit as Kelvin is to Celsius. Got to get that order right. And we use, for the conversion, degrees Rankine is going to be equal to degrees Fahrenheit plus 459.67 degrees. Then secondary quantities are produced by combining various multiples of the secondary quantities, or taking them to a certain power. So secondary quantities, again, are determined from primary quantities. These are things like density. Secondary quantities. Some examples of these, and I will do the same thing. Well, I won't do them in terms of SI and British, but you can have things like velocity, force, stress, and density. These are examples of secondary or derived quantities. And I'm going to use, through the course, I'm going to use this symbol right here. Sometimes I'll use this. This means has units of. And this, again, will be very important when we get to dimensionality and similitude later in the semester. This means has units of. So velocity will have units of LT to the negative 1. So length divided by time, that's velocity, of course, just illustrating the idea of a secondary quantity. Force will have units of MLT to the negative 2, or MLT to the negative 2. Although sometimes we actually reconstruct this using force as a primary quantity instead of mass. Either one is actually fine. Stress, you just can't combine them. Don't worry about that. We'll get to that later in the semester. Stress, sigma, has units of MLT. It's force over area. So MLT to the negative 2, L to the negative 2. If you work through the definitions of force equals mass times acceleration divided by area, and you will get MLT to the negative 2 times L to the negative 2, or simply L to the negative 1, T to the negative 2. And then density, rho, has units of ML to the negative 3. Okay, so let's move on to talk about a few fundamental fluid properties. I want to define a few very basic fluid properties that we'll be using throughout the semester. Fundamental properties of fluids. There's just a few that I want to list very briefly that you're probably already aware of. You've probably heard them before, but it can be useful to get a refresher. So the first one is going to be density. And for this, we are, of course, going to use the Greek letter rho for density. And density is, now, sometimes we, in sort of mix up, or sometimes we use the word density when we actually mean specific weight. But in this class, it's very important to be very precise in our language. So density means mass per unit volume. Does not mean weight or force per unit volume. It means mass per unit volume. So this is, again, a mass characteristic. For the British system, it's going to be slugs per cubic foot. And then for the SI system, it's going to be kilograms per cubic meter. And water is approximately 1,000 kilograms per cubic meter, or approximately 1 kilogram per cubic decimeter, or approximately 1 kilogram per liter. So that's something that can be useful to keep in mind. Although the exact value will vary based on the density, the pressure, the exact value density will vary based on pressure, temperature, etc. But again, water, approximately 1,000 kilograms per cubic meter, approximately 1 kilogram per decimeter cubed, or approximately 1 kilogram per liter, if that's a unit you're working with. Then specific weight is also something very important that you need to know, and this is gamma, the Greek letter gamma. This is, again, the Greek letter gamma, so you're probably already fairly used to working with Greek units or Greek letters, and you're going to get very good at it through the course of this semester. This is the weight per unit volume. This is the weight per unit volume, so it's a weight characteristic. In the British system, it's going to be pounds per cubic foot. pounds per foot cubed, or simply PCF. You'll sometimes see me use that abbreviation. And in the SI system, it's going to be newtons per cubic meter. And gamma of water is approximately 9.8. So this is where we have to multiply by G, basically multiply this by G, 9.8 kilonewtons per cubic meter, or 62.4 pounds per cubic foot. That's something you might want to memorize. The density of I'm messing it up. Again, it's very easy to use the word density when you use specific weight, but we will try as we go through this course to be very precise about using the appropriate label when referring to fluid properties. I would encourage you to memorize this, and this, or maybe at least this and this, that the specific weight of water is 62.4 pounds per cubic foot. And of course, recall that gamma is going to be equal to rho times G. The specific weight of a fluid is going to be equal to its density times the acceleration due to gravity. And finally, let me introduce a third property, specific gravity. If I said specific gravity here, sorry, I meant the acceleration due to gravity. Specific gravity or SG, looks like a 6, let's erase that, or SG, specific gravity is simply the ratio of the density of water, or density of a fluid to the density of water. This is the ratio of the density of a fluid to the density of water. The density of water at a specific temperature. Typically 4 degrees Celsius. For liquids. Oh, actually, sorry, just typically 4 degrees Celsius. Now, it's important to keep in mind that this is unitless. So, although it's for liquids, we're going to use water at some temperature, and rho of water, if we need to know this, at 4 degrees Celsius. So at 4 degrees Celsius, let me write this a little better. Rho of water at 4 degrees Celsius is 1,000 kilograms per cubic meter. So it's going to be the fraction of that, or 1.94 slugs per cubic foot. Slugs per cubic foot. And so the specific gravity for liquids will be based off of comparing it to water. Rho over rho water, or, which will also be equal to gamma over gamma water. You can use either one, whichever is more convenient. So I would really encourage you to know how to work an exchange between specific gravity, specific weight, and density. For example, in certain problems, certain exam problems, I won't say, oh, here we have a fluid. You may have to use the quantity density, but I may just tell you that this fluid has a specific gravity of 1.8 or something. And you will have to convert to density to put it into the appropriate equation. And it is going to be temperature dependent, so the specific gravity of fluids can change with temperature. In other words, different fluids, so for example, if I increase the temperature, the density of fluids generally decreases, but they don't necessarily all decrease by the same amount. So if I double the temperature of water, if I have a fluid, maybe oil and water, I double the temperature of each, maybe one increases by 1%, another increases by a different percent, so the specific gravity won't necessarily be constant. So I should say, sorry, I meant to write here, temperature dependent. temperature dependent. And this is how you measure this or calculate the specific gravity of a liquid, but we also want to be able to do this for a gas. So for a gas, and again, let me label this for liquids. But then for a gas, I'm going to have a different relationship or different definition. And notice again, because we're dividing density by density, specific gravity is unitless. So that's important to keep in mind. So instead of using water, because we don't want to, the whole idea of specific gravity is comparing the density or the specific weight of a fluid to a more familiar fluid. Now we could use water vapor, but that's not a very familiar everyday type of fluid. So instead we use air, normal air at 1 atmosphere. So for a gas, we're going to say the specific gravity of a gas is the density of gas divided by the density of air. So rho gas over rho air. And this again is for liquids. And here, this will be important to keep in mind, or important to know, rho air is going to be, we can define it for our purposes. Obviously it can change with different pressures and things like that and elevations, but for this I'm going to consider usually that the density of air is 1.205 kilograms per cubic meter. And finally for liquids, an interesting thing to be aware of or to note, if the specific gravity of something is greater than 1, it sinks in water, and less than or equal to 1 floats in water. If it's exactly equal to 1, it's neutrally buoyant. All right, that will conclude my brief introduction to fluid mechanics. We will continue through this on Friday, but I just wanted to give you a brief introduction to what fluid mechanics is, what exactly the definition of a solid, liquid, and gas are, definition of a fluid, and some simple material properties. I will see you in class on Friday, and as always, thank you.